Hi class, in this recording we're going to talk about electrical activity of the cells. We're getting ready for the action potential discussions and the details of how an action potential works. For this discussion, we're just going to talk about electricity and electrical activity in a more general sense within the central nervous and peripheral nervous systems. So first, let's talk about some big concepts. When we think of electrophysiology, this is going to be the study of the mechanisms for generating and propagating electrical activity within the cells. Electrophysiology is, as you may imagine, a rather complicated topic, and we use it for communication within the nervous system and contractions within the muscular system. It's all going to depend upon that electric potential. And when we think of electric potential, I want you to think of voltages, electric potential energy. Now, in a really broad sense, when we think about electricity, electricity is the movement of charged particles. And within our body, we have charged particles on the inside and the outside of our cell membranes. This is going to polarize our cell membranes and give them some electric potential even when they're at rest. This electric potential, when the cell is not really doing anything, is called resting membrane potential. As a general rule of thumb, cells are going to have more negative particles on the inside than the outside. So there's a net negative charge on the inside of the membrane. Most of the negative particles that are stuck on the inside of the cell, they're stuck. You can't get to the outside of the cell. There's going to be anionic proteins, very large negatively charged proteins on the inside of the cell. Now, as we look at electrical current will be the movement or the flow of those charged particles from point A to point B. In our bodies, sodium and potassium are the two charged particles, sodium ions and potassium ions, that do most of the movement. We have special gates that can open and close. These gates are going to be specific for both sodium and or potassium. And we can open and close these sodium and potassium ion channels with different methods. We can have physical stimuli, we can have electrical stimuli, or we can have chemical stimuli. Oh, excuse me, I missed your point. Oh, sorry about that. You need to have good posture when you're making lecture recordings, because if you slouch, you start to yawn. And as we look at this electrical current, it's going to enable cells to turn on and off. If we have an electrical current traveling down the cell, it's going to have the charged particles with lots of movement. If we don't have that electrical current, we're not going to have a lot of movement of the charged particles because the gated channels are going to be closed. So let's talk about the resting membrane potential in more detail. As we think of the resting membrane potential, it's existing because we have an unequal concentration, an unequal amount of electrolytes. When we think of these electrolytes, those electrolytes are dissolved salts. And I don't mean table salt, I mean dissolved ions. So sodium chloride, potassium chloride, magnesium chloride, lots of chloride-based salts are out there in our bodies. And these dissolved salts are going to be moved in the extracellular and intracellular fluid unevenly. And we have these uneven distributions of these dissolved ions, giving us a resting membrane potential because of three different things. We have ions moving with our concentration gradients. We are going to have the plasma membrane being selectively permeable. And this is the big one right here. The selective permeability of the plasma membrane allows some ions to move in and out easily. Other ions have a more difficult time moving in and out. And then as we're looking at our, sorry for yawning so much there, as we're looking at our anionic proteins, negatively charged proteins stuck inside of the cell, those anions inside of the cell are going to draw cations from the outside to the inside of the cell to help influence resting membrane potential. Let's focus on potassium ions, the single greatest influence, or the single most important ion for resting membrane potential. Our cells have lots of potassium leak channels. So we're very permeable for potassium. And potassium is going to keep leaking out until cytoplasmic anions. So when we think of cytoplasmic anions, ooh, that didn't look good there. Cytoplasmic anions, there we go. Those are going to be shown in green down here, large protein-based anions. are going to keep attracting potassium and bringing it back in. And eventually we'll have some equilibrium where we'll have a higher concentration of potassium inside of the cell. The potassium tries to move out of the cell with this concentration gradient, and then the anions in the cell pull the potassium back in, and we'll reach an equilibrium point where we'll have about 40 times more potassium intracellularly compared to extracellularly. Those cytoplasmic anions are stuck inside of the cell. We have some of them are polyatomic ions like phosphates, sulfates, small organic acids, but really it's that protein. The protein is the big one that cannot get out. As we're looking at the resting membrane potential, sodium ions also play a role. Not as much of a role as potassium ions, but they're still significant. And when we look at sodium, we're going to have more sodium in the extracellular fluid, about 12 times more sodium extracellular than intracellular. So what does this mean? This means that instead of sodium leaking out like potassium does, sodium has a tendency to leak into the cell. This sodium leaking in is going to make the inside of the cell membrane more positive. Sodium ions have a positive charge, and as we add more positive charges to the inside of the cell, as the sodium moves into the cell, the sodium makes the inside less negative than it would have been otherwise. To help control concentrations of sodium and potassium, to maintain the concentration gradients, we need a sodium potassium pump. And as we look at our sodium potassium pump, it's going to move 3 sodiums out of the cell, because we need to have a high concentration of sodium out of the cell, for every 2 potassiums that it brings into the cell. So 3 sodiums out, 2 potassiums in, and to do this exchange, it needs to burn through the energy of 1 ATP molecule. And these sodium potassium pumps are constantly working to maintain resting membrane potential. They use up approximately 70% of the energy of the nervous system. And if we think of our nervous system, it uses up about 20% of the energy in our bodies, or 20% of our basal metabolic rate. So the sodium potassium pump of the nervous system uses up 14% of the calories that we consume. Wowza, that's a lot. As we're looking at the sodium potassium pump, it means that we need to have a high supply of glucose and oxygen being supplied to nervous tissue, so that we can create lots of ATP for the sodium potassium pump to function. And if we're looking at this, we're going to dump 3 positive charges out, 3 sodium ions out, and bring 2 potassium ions back in. So we're going to result in a net increase in the negative charge on the inside of the cell. We're losing more positives than we're gaining, and this is going to cause the cell's resting membrane potential to become even more negative. That's all we have for this recording. We focused on the ions and the pumps of the resting membrane potential. If you have any questions, please feel free to post them on the class discussion board or shoot me an email. And as always, happy studies.